Hello, this will be our third electronic structure video, and we're picking up again here on slide 31, and we'll go from there. So we just talked about in the previous video the Bohr model and how the Bohr model only works for something with one electron, so it's pretty limited, but it introduced some really important ideas. This idea of the energies only having certain allowed levels, that is that they're quantized. Those quantized energy levels are described by quantum numbers. So one picture we looked at before again has very weird. Don't know why we got that kind of problem with the drawing. Let's try that again. Okay, now it's all showing up again. All right, so if we have an energy of 0 up here, and then going down from that into negative energies, you have your different levels. So the n equals 1 level is down here, and the n equals 2 level is there, and so on. And as you go up, they begin to get closer together. And the energy that we see, the lines in the spectrum arise from electron transitioning from, say, maybe getting excited to the third level and then falling back down to the second level, and when it falls back down it gives off some light. The energy of that light is equal to the difference of energy from 3 to 2. And we can calculate all that, and we know that that's equal to hc over lambda, where lambda is the wavelength of that, so we can calculate those things. But the important idea is that you can't have like a 3.5 level or a 2.2 level. You've only got certain allowed energies. So that kind of suggests itself going on into this idea of a bigger theory that works for more numbers of electrons, although we do have to invoke a lot of approximations to make it work, and that's called quantum mechanics or quantum theory. Quantum mechanics. Quantum mechanics is the term. Now, before we talked about the wave-particle duality, the idea that light particularly could be seen as either a wave or a particle, we're kind of turning that around and saying, okay, let's think about a particle like an electron. If a particle like that's moving really fast, and it's really small, it could behave like a wave, and we're going to, quantum mechanics is essentially applying that idea whole hog on this. And we're not going to get into the details of the mathematics, which are quite complicated, but we are going to talk some of those. So you see some of your learning objectives here for this section. So again, the idea that particles and waves, for very small particles, may act like waves, and even we can think about very big particles having waves, but that wave characteristic is not very important with them. And if you look at Professor Dave's video on that, it's very good. Now, another idea that came up was something called the Heisenberg uncertainty principle. Werner Heisenberg is the person who came up with that. And it's an interesting idea. It says that our ability to know information is limited to a certain amount. And so basically he talked about position, which we might describe as x, and its momentum. Momentum is given the symbol p. That's equal to the mass times the velocity. So we could say the position and the velocity. And basically the more precisely we know the position, the less well we know the velocity or the momentum. If we know the velocity or the momentum really well, then we don't know the position very much. So it's this idea that you can't determine simultaneously and exactly both the momentum, which again is velocity and also can be thought of as energy of the particle, and the position. So when you apply this to looking at atoms, we're going to see that we talk not about where the electron might be, but where the electron, the region in which the electron is possible to be. So anyway, so again, there's a section of these next bit of slides that have the Dr. Russell makes reference here to the pages of the text. I assume that's the PDF printout of the text. And then you can relate those to the over here on the side. We have this set of questions here for slides 36 to 56, so you can relate that back to that as well. So that's basically what he's pointing to. All right, so the idea is that the energy of the electron is quantized. We've only got certain levels, and it can only go from one level to another. It can't hover between a level. And we're going to quantify, or we're going to classify these states with quantum numbers. And the first quantum number we talk about is the principal quantum number, which is n. N can be values of the positive integers, so 1, 2, 3, 4, 5. N can't be 0. It can't be half or anything like that. Think going back to looking at kind of the hydrogen, the Bohr model of the hydrogen idea, you can see sort of how that N concept applies there. We're going to relate it all to the periodic table in a little bit, which is a good way to think about it. Now, you then are going to have some other quantum numbers that relate to this. And as I said before, your orbitals are going to be these three-dimensional regions in space. So we don't talk about an orbit, but an orbital. And that three-dimensional region is where you're likely to see the electron. So the second quantum number is L, and L's values start with 0 and go up using the positive integers to a maximum of n minus 1, depending on whatever the n value is. So again, if you have n equals 1, you can have L equals 0. If you can have n equals 2, you can have both L either be 0 or 1. That's called a subshell, and if L has a value of 0, we call that an S subshell. If it has a value of 1, we call that a P subshell. If it has a value of 2, we call that a D subshell. And if it's 3, we have an F subshell. Folks say some people do fine is one way folks remember SPDF. So, and again, this is the same thing I just wrote on the previous slide. Now, the wave function is what we use to describe the electron that we're thinking of as a wave. And the wave function is usually basically thought of as being a product of some other functions that depend on n, L, m sub L, and m sub S are quantum numbers. And the wave function, the square of the wave function, that's the Greek letter psi, by the way, psi. That square is the probability of finding the electron in a given area. And then another thing to know is that the energy of the electron is going to be a function mainly of n and L, of the n quantum number and the L quantum number. Now, this slide simply says that if you look at a graph of wave function versus R, you might have a wave function that goes up and then comes down and then goes back up again. This point here where it's 0, that is what they call a radial node. Okay, and again, R is going straight out. This is the distance from the center of the atom. And you can relate that to the value of n minus L minus 1. So a 1s orbital has 0 nodes, so it looks something like this. 1s orbital is going to pretty much go up and come down like that. A 2s orbital is going to look like the one on the previous slide, where it comes down once. A 3s orbital is going to have 2 nodes in it, and you'll see some pictures of those. So here you go, this is our 1s orbital. So this is our 0 nodes, 1 node, and 2 nodes. And this is our 3D graph of the likelihood of finding the electron. And so what you see is an s orbital depicted as a sphere, but sometimes that sphere is not uniform, and it might even have spots in the sphere where the electron can't be. And it's kind of weird, it's like the electron can be here, it can be here, but it can't pass in that point between them, which is a very weird thing for a particle, but actually makes a lot of sense for a wave. So the diagrams, the figures of the subshell type orbitals are given on this next slide. So here you have your s orbitals; they look like a sphere. Your p orbitals, they say, looks like a dumbbell. Your d orbitals look like typically 4-lobe dumbbells, except for this weird one right here in the middle that I like, that's a dumbbell with a donut or an annulus. And then your f orbitals are really weird. Oftentimes you have 8-lobe dumbbells. You also have the double donut one there. So some kind of cool 3-dimensional graphs, but that's the regions the electrons exist in. Okay, so we said 4 quantum numbers. The next quantum number is m sub l. So again, we say m sub l. And what this does is it specifies the orientation in space of the orbital. And the m sub l value depends on the value of L. So what you can do is you can start with negative L, start adding to negative L, so negative L plus 1, negative L plus 2, etc., etc. And then eventually you'll get to 0, and then you go on and you'll have increasing values up until you get to L minus 1 and L, like so. Basically, it breaks down this way. If you have an s orbital, L is equal to 0, m sub L can only be 0. If you have p orbitals, L is minus 1, so m sub L comes from the set minus 1, 0, plus 1. And I should make that set notation as well. For our 5 d orbitals, L is 2, so m sub L can start off as negative 2, negative 1, 0, 1, 2. And then when you get down to the f orbitals, L is 3, so m sub L can be negative 3, negative 2, negative 1, 0, 1, 2, 3. And what that corresponds to, again, is the number of L orbitals that you have for that energy level. So again, N and L are what give you the orbitals. If you have orbitals that are at the same level, they're called degenerate energy levels. So we'll see energy diagrams that look like this, where you have a 1s and a 2s and then 2p, and of course that 1s there refers to n equals 1. The s refers to L being equal to 0, and up here n is 2, and the p tells me that L is equal to 1. And you see that these 3 orbitals here have m sub L values of negative 1, 0, positive 1. Here m sub L is only 0, only have 1 value for the s orbital, so we only have 1 orbital available there. So again, it's the N and L values, and you'll see the diagram here. This is the diagram like I was drawing. One thing to notice is this little situation up here in this diagram. 4s is actually before 3d. It's lower in energy than 3d. And so again, it's not just N, which would be the 3 and the 4 that matter. It's also the value of L. In 4s, L is 0, and 3d, L is 2. So that has an effect on those energies. There's a final quantum number, which is the electron spin. It's called m sub s. And the good news about that is there's only two possibilities, minus 1/2 or plus 1/2. Electrons have what are called a half spin, and you can think of it whether it's spinning clockwise or spinning counterclockwise. We write that sometime as either an up arrow or a down arrow, like so. You'll see those abbreviations used. So again, here's the spin quantum number like we described on the previous slide. All right, so there's some rules in quantum mechanics. We've got the Pauli exclusion principle here, and it tells us that hold on just a sec here. It tells us that for the values of NL, M sub L, and M sub S in one atom, no two electrons can have the same four quantum numbers. What this also means is that we can only have two electrons in one orbital and they have to have opposite spins. So if we were writing an orbital and we put two electrons in, one spin up and spin down, that's okay. If I wrote two electrons both spin up in the same one, that's not okay. That's one of the rules, consequences of the Pauli exclusion principle. So, and that's pretty much what this slide says. So here's a big table that tells you about the different quantum numbers, their allowed values, and what that results in terms of the physical meaning category there. All right, and we will break this video at this point, and we'll be back with more later.